Okay, yes, is a video time again for year 12, 2008, 007 clip. Yeah, the reason I'm trying to do this today because I like to give you just a catch up. So for those exercise, I remember that like for some crucial concept I try to explain in the class is equilibriums. Equilibriums that would related to things that we do, we have to find out what is the equilibrium constants. And we try to find out equilibrium constant can be found out by a graph like this, which is like talking about the concentrations over time. And you'll find that for initially, the reactants normally have the highest concentration, it start to drop and forming product. And the product concentration is supposed to be zero initially and it slowly catch up. And at a certain point, all the concentrations of the product and the reactants becomes constant. So when they're not moving, at this particular point, we call them equilibrium. And these equilibriums, because the concentrations stay the same, we can do a calculations based on the concentration change. And the concentrations of the product divided by the concentration of the reactants is a constant. And this one is kind of project or correlated to the coefficients of the equations of the chemical equations. Then it come up into a formula. The equilibrium constant is equals to yeah, product coefficient divided by the reactants. So now I've got a question. Remember, like, yeah, I'll give you a question to go through. So to help you remember what we've been doing, I'm just using this example again. So for the formation of ethyl acetate, which is the product on this side, can be reacting between what we call them CH3COH with ethanoic acid react with CH3CH2OH is ethanol. Ethanoic acid react with ethanol can make what we call ethyl acetate, and this process causes condensations. In this particular condensation, we've got a K values, and the K value, what is K value? The K values, the value of K, which is this one there, equilibrium constant. Equilibrium constant equals to 4. If you're looking at the graph we've got it here, it means that if the reactants dropping and the product increasing, at a certain point they becomes constant. And this constant with the coefficient we find we'll be able to do equals to 4. Since the equation that we've got here is 1 to 1 to 1 ratio, then the K can be calculated extremely easy with the product CH3COOCH2CH3 times by water. Yes, divided by those two reactants CH3COOH with CH3CH2OH. So by doing this equilibrium constants, the reactants times each other divided by the product times each other divided by the reactants times each other. And because the coefficient is all to the power of 1 to the power of 1 to the power of 1 to the power of 1, and we are very happy to see this can be calculated, can be easily calculated without square or cube or blah blah blah. Now, what do we want for this exercise? We've got 6 different individual experiments. Well, you can look at that 6 experiment is at different stages of the equilibrium, approaching equilibrium. Some of the experiment may be right here. Some of them may be right beyond at the end. Some of them would be like close and closer to the equilibrium. Some of them may go beyond. So if we here looking at this, your job is to calculate based on the equations here and see whether they equals to 4 or not. If they equals to 4, that means it's at equilibrium. If they're not equal to 4, the value, we don't use K anymore because K is just at equilibrium. And we try to calculate, we assume, we call this Q. And Q means a quotient of your product over reactants. And Q for experiment 1 is 1 times 1 divided by 1 times 1, which is equals to 1. And this Q equals to 1. The Q is the stages of this experiment. 1 is smaller than 4. It just means that at experiment 1, you are approaching to the equilibrium, but not yet, right? So you are trying to say whether in which experiment has equilibrium been achieved. First one, not. The first one definitely is not at equilibrium because the value is only equals to 1. How about the second one? If you look at the second one, at this particular stages is 2 times 8, the product, divided by 4 times 0.5. 4 times 0.5 cancel each other is equals to 8. 8 again, that's 4. So definitely that is not at equilibrium. But one thing that we want to find out is the second one. In which direction the equation is going to establish for the equilibrium. Whether 1 and 8 tells you particular information. If K is equals to 4, Q is equals to 1, that means your, what do you call them? Your K is bigger than Q. On the other hand, if you have Q is equals to 8, and that means your Q is bigger than your K. So there's two situations, and we have to know one thing. If K equals to but bigger than Q, that would mix the equations going forward or backward. Let's say A plus B becoming C. If K is bigger, K is bigger than the stages, what does that mean? In order to make a bigger K, that means we want to have a bigger K to achieve equilibrium, EQ. In order to make a bigger K, we look at the equation is product over reactants. In order to get a bigger values, if we want to get a bigger values, definitely P need to increase. If we don't have P increase, then you would not be able to get a bigger number. So therefore, the reaction need to become more product. So more product is needed. If more product is needed, that means the reaction is going to be forward. You need to have more forward reaction to achieve equilibrium. It's going towards to the right-hand side. Is what we predict if K is bigger than Q. On the other hand, if we want Q is bigger than K, that means by looking at the equilibrium constant P and R, we do want to have a smaller K this time to achieve equilibrium. A smaller K means that we need to decrease the product but increase the reactants. If we decrease the product, increase the reactants, it implies that more reactants is needed to achieve equilibrium. So we can come into conclusions the reaction would move backwards. And when it moves backward, it means that it goes to the left-hand side. Okay, so these particular questions, you'll find out, okay, going forward, going backward, and we've got the calculations related to it. And 3, 4, 5, 6, you can enjoy it, whether basically if it equals to 4, it's at equilibrium. If they're bigger than 4, it's going to be backward. If it's smaller than 4, it's going to be forward. Right? It's easy to see by just doing these particular questions. And there's some other questions you can involve with it, like the other one. Excuse me. Like the other one there. Question 12. So let's crop this question 12, and you should have this in your class. So if we try to do question 12, so what do we do in here? A question 12 saying that we have a reactions. 3.5A is produced in a 500 ml flask, and once allowed to reach equilibrium, the concentration to be found to be 2 mole per liter. We need to find out the equilibrium constants. Okay, seems like it's not enough information. What can we do? We always start with 2A, forward to backward, 2B plus C. Then we know that K constant can be calculated by the product B squared times by C1 over A squared. So if that is the basic thing that we know, what do we want is to think about what over time, what is happening. Let's have a look at the graph. If we have A initially, this is the concentration of A. We have how many moles? 3.5 moles in there. There's a 3.5 moles in here. And that means that one's going to drop. And once it got dropped, it will become stable when it's reached equilibrium. A and B would increase. Because A and B is 2 to 2 ratio, the number of A drops would be equals to the number of B increase. However, the C is only 1 to 2 ratio. The amount of C would be only half of the A that dropping. So if we can kind of like in your mind knowing this is your equilibrium, and we know that the particular ratio would change according to them, the information give us a little bit more information is at the end we only have 2 mole of A left, right? 2 mole of left. So this particular point there is 2 mole. Then we should set up a particular tables called A, B, and C. It's 2A, 2B with C. Initially, we have 3.5 mole, and we have 0 and 0 over there. And change of mole going through the process, it dropped. So this is initial mole and change of mole. Initial is 3.5. The change of mole is 3.5 down to 2. So this is 1.5. As 2 and 2A and B is 1 the same ratio, when it dropped 1.5, our B would definitely increase by the same thing, 1.5. So increase 1.5. However, the C, there's only half of it. So half of 1.5 is 0.75 only. Right? So that is the change of mole. Then, as equilibrium constant, calculate by the concentrations. And we need to find out the concentration of each. Concentration is controlled by the volume. And we need to make sure that we pay attention to the volume that's happening in there, which is 500 ml, 0.5 liter, 0.5 liter, 0.5 liter. Before we find out equilibrium constant, we have to change all of them into concentrations. The concentration for the first one is the number of mole divided by volume, 1.5 divided by 0.5 here, then is sorry. Before we do concentrations, we need to calculate the number of moles that left over. 3.5 take away 1.5, I have 2 moles left. 0 plus 1.5, I have 1.5 increase. 0 plus 0.75, I have 0.75 mole increase. Then we calculate the concentrations. As the concentration is equals to N over V, this is 2 divided by 0.5, against that is 1.5 divided by 0.5, and the last one is 0.75 divided by 0.5. So divided by 0.5 means times it by 2. So the concentration here would be 4 m. That one would be 3 m. That one would be 1.5 m. Now equilibrium constant is equals to b squared times c over a squared. B squared is 3 squared, c is 1.5 divided by 4 squared. If you look at your calculator, then the calculator can be doing, do I have calculator here? Calculator. 3 squared is 9 times 1.5. 13 divided by 4 squared is 16. And the answer is 0.844. 0.844. 0.844. That is our answer. And the last thing that we need to consider for equilibrium constant is the unit. The units change every time. As everyone here, that's like b squared means it's m2 there, and c is just m. So basically the unit above is m squared times m, the one that's m2. So if we know that this cancel each other, the one that left over, the equilibrium constant would be 0.44 m. Right, so hopefully I'll give you a revisions on those equilibrium. Then next time when we start doing the course, and we should have a better understanding of how things change over like in there. Okay, thank you.